Welcome, everybody. Good morning. Welcome to our machine learning seminar. Today, we'll have a pleasure to have a talk from Oscar Castro, who is a researcher in the Luxembourg Institute of Science and Technology, and who will give a talk on the topic that is presented on the screen. Oscar, the virtual floor is yours. Please go ahead.
Okay, thank you, Jakub. Good morning, everyone. I'm going to present the name of this presentation is the multi-target compiler for the deployment of machine learning models. And let's start. This is the content of the presentation. I'm going to start with the introduction to give some background on the subject. Then I'm going to explain a little bit about the design and implementation of the compiler, the empirical evaluation of the compiler, and then finally to end with the conclusions. So, okay, if I understand correctly, you are most of the audience is familiar with data science and machine learning, but anyway, I will try to give some background and some perspective on this. Nowadays, there is a great interest in building applications which are infused with machine learning models. And as we know, there are many different tools to build machine learning models, especially languages such as R and Python. We have many libraries, but there are other cases, Weka, Canim, SAS, SPSS, TensorFlow, Keras, PyTorch, etc. So let's just stress that this task of modeling is normally done by data scientists, which is a role closely related to mathematics, statistics, and especially the domain knowledge of the data. And this data scientist role use tools and languages for rapid building and prototyping, and they also work in a more or less flexible environment where they are constantly experimenting. And their main objective is to create the best possible model, of course, given some threshold in terms of performance of the accuracy of the model. In this slide, this is more or less the steps that we follow when we are working with data and we're trying to create a machine learning model or a predictive model. So we start. This is based on the CRISP-DM modeling process, which is a standard for modeling. So we start by the task of understanding the business and trying to understand what we are going to try to achieve with data and with predictive modeling. Then we go to a phase of data understanding, trying to understand the domain of the data. Then we go to a step of data preparation where we collect data from different sources and we do that data engineering task, data wrangling task, and we prepare the data to fit the machine learning algorithms. Then we go to the modeling step where we actually use the tools that I just said or the libraries that I just mentioned to create those models. And we can go back to data preparation if necessary. Or we can go directly to evaluation, which means that we will check if this model complies with what we are expecting in terms from the business understanding that we have. Let's say we want a model with above of 85% of accuracy in our predictions. And if that's the case, we go to a deployment task. So here we go from historical data, we follow some steps, and we got a model. And after that, we got a machine learning model, which is a function. I mean, it's not that we adhere strictly to the steps, but more or less we follow this approach when we are working in these kinds of projects. So now let's talk about the center of this, which is the deployment of machine learning models. Once a model has been built, it must be deployed to a production environment. This means this production environment is mainly a software or an application where the model is going to put into operation for an intended use. And it's very important to remark that in production is where the model generates value through the predictions that made on incoming data or new data. Prediction is also known as scoring or inference. It depends on the domain, but normally it refers to the same, to generating predictions or generating an output on data, on new data or on incoming data. And we can define deployment, but as the general process of taking a model, which is a mathematical function, to a specific operating environment where it is available for its use, which is software. And this graph is just a very high level concept of this. On the left side, we have a software unit that contains the predictive model or the machine learning model that will receive that data and will return predictions to the end user application. In this case, in this graph, it's separated, but it can be depending on the architecture of the system. It can be outside or inside, and we will see some examples of it. So, building applications integrating machine learning models, it's a challenging task. It can be a challenging task. In an maybe this makes more sense in an industrial environment, but because if you are a data scientist or you work in an academic environment, you are more or less aware of this. But software in production is developed and maintained by software engineers, which are in nature a different role to data scientists. So software engineers are experts in software building tools, IDEs, SDKs, frameworks, etc. And their aim is to build software following requirements and quality attributes. So this is just to make a difference between software engineers and data scientists. And both processes are done sometimes, it's not always the case, but are done in different languages and always in different environments. The integration of these models with other bigger systems, let's say, must comply with a software design or a software architecture that normally data scientists do not take into consideration, and they don't have to. And this is an interesting figure that I had checked since 2019. Where it says that the 60% of machine learning models are actually never deployed to production. This is a Gartner report, and I just each year I check this, and the figure for this year is 53%. So it has improved, but still it's more than half. So there are many reasons why machine learning models are never deployed into production, but one of them that we try to address with this work is technical difficulties. There are different common deployment approaches. I try to cover most of them. Of course, it's not an extensive list, but more or less we can more or less, we can group them like this. The first, and I think that the most common, is using a pipeline, which is connecting the software in production with the same modeling tool that the model was created. I think that this is the most common and the easiest way. There's another one which is in database, which is not so common, but is possible. There are some modern databases that include machine learning models within their system, so you can build and deploy the models with data inside the database and just use them as an SQL query. For example, there are some Oracle databases or Teradata databases where you can do that. The other one, it's manual coding, which is basically translate manually whatever you did in some modeling tool into a programming language. And the other one is the IoT or edge computing, which is basically one-to-one compilation. This is another common approach, especially for deep learning models, because they require a lot of computation. So what they have done is you have one input for one format of a model, and then you have one output, for example, for FPGAs or another special hardware. If each one of them satisfies, let's say, some requirements or some restrictions for some systems, but there are some drawbacks that we can name for each one of them. Especially in the using a pipeline follows a client-server approach, where the server is the modeling tool, where the model was created and it was also deployed with this tool. So somehow they must communicate with the software in production, and this can become a bottleneck for the whole system if you use R or if you use Python. As you might know, those languages are not known for being really efficient in executing heavy computational stuff. Additionally, scaling a pipeline can become a pipeline jungle, which has been documented in different papers, and they are difficult to maintain over time. In database, approaches are very specific because you must use whatever they give you. In terms of there's a limited amount of techniques that you can use versus, for example, R and Python, which are normally publishing new libraries, and you can use state-of-the-art algorithms to create new types of models. So they are specific in those regards. Manual coding, well, coding is a labor-intensive task, which is prone to errors. You can have a model with hundreds or maybe thousands of floating point coefficients, so it's really hard to do it. You will easily commit a mistake. After all of this that we analyze, we can we focus on trying to solve the manual coding approach. So we can formally describe our deployment task in the way that we are going to address it as the following. Given a predictive model A, which is a computer-generated mathematical function expressed in language L, we want to generate A prime expressed in a computer programming language L prime, where A prime is semantically equivalent to A. And as we are already stated, machine learning models can be formally defined, and we use modeling tools to build them, to generate them. We can algorithmically transform them by using a compiler. So this is where the compiler becomes a proposition for this problem. And during this project, we developed a multi-target compiler to translate these machine learning models into source code, and we can automate this deployment to production environments. This is a high-level view of how the compiler should work. We have model description and we have a target language, and those are the inputs to the compiler, and the output of the compiler are simply source code, where you can use the function prototype just to invoke a function and send the data and embed it in your application. This is the design of the multi-target compiler. The multi-target ability is given by this design because we separated, we use compiler theory to have a front end separated in a front end, an intermediate representation, and back end. The front end is in charge of translating a definition of a machine learning model into the intermediate representation that we define. In this intermediate representation, we can apply optimizations to the execution of the model. And then this intermediate representation is the input for the backend, and each backend is in charge of converting this intermediate representation into a final source code and ready to be implemented. This is the general design, or the general approach that we defined at first, and we also did an implementation. This is just an example of an intermediate representation template. We use templates for the different types of machine learning models. For example, this is a program for a neural network where we have the definition of the name of the function. We have all the different variables that are going to use it as parameters or as inputs to this model. We have a variable declaration list, we have some statements, we have the feed-forward algorithm, and at the end we are going to return a prediction. These representations are quite big. This is why I split in two parts, but let's just remember the feed-forward is just iterating over each layer, and then in each layer iterating over each neuron and doing all the computation required to get the prediction. This is the implementation that we did of the multi-target compiler using the design that we previously mentioned. On the left side, we have the modeling tools. This is a purely design decision of using a standard for representing machine learning model, which is called the Predictive Model Markup Language, PMML. The advantage of this is that we can use R, Python, Kenim, and another set of compatible tools. You train your model, and then you export your model into PMML, which is an XML-based standard. So using this approach, I only implemented one front end, but this front end is compatible with many modeling tools. And then the front end transforms PMML described models into an intermediate representation where we have templates for different languages. And I developed several backends for this. One in C for Java, and I also developed for user-defined functions in MySQL and Vertica. And I also have some versions of C with OpenMP to use all the cores of CPU, and also CUDA C for using the GPU. What this allows me is to add backends without modifying any of the rest of the code, or adding a front end without modifying any of the rest of the code. So that gives the ability to the compiler to be multi-target. After the implementation of this compiler, we did an extensive empirical evaluation. First, we validate the correctness of the compiler by comparing the predictions generated by the original tool where the model is created. This means that we generate predictions with the modeling tool, and we generate predictions with the generated code by the compiler. And if those are equal, then it means that our code generated or generated code is correct. And the most extensive, well, the most important part is that we also test the efficiency of the execution of the predictive models by the code generated by the compiler. This is, well, the first thing that we did is that with R, we created some general linear models, then exported to PMML, then used the compiler to generate C and Java code, and we compared the execution with R. We know beforehand that given that R is an interpreted language versus C and Java, which are, well, C is compiled and Java is compiled and then used with the Java virtual machine, that they are going to be faster. And this is the case in many of the experiments that we did. Here I'm presenting 3 of them. The abbreviations are for the name of the datasets. Those are in the at the end of the presentation. But basically, in the y-axis, I have the elapsed time in seconds, and in the x-axis, I have the unscale factor for the size of the dataset. So we tested with the original dataset, and on all the numbers that you see on the x-axis is the increments that we did to that dataset. Of course, C it's faster than R, Java 2, but in general, C it's faster. So this is our baseline to be able to say, okay, the generated code is faster than if you use the modeling tool where the machine learning model was created, right? In the next experiment, we follow a similar approach using R, exporting the model with PMML. Just in this case, I generated a support vector machine model with a binary class. And then this is the input to the multi-target, and I generated C code, sequential C code, which uses one single core. Then I generated C, sorry, with OpenMP for a multi-CPU approach by using multi-cores. And then I also generated for CUDA-C to use the GPU. And here it's the same. The y-axis is the time in seconds, and the x is the size of the data in gigabytes. So we can see that by far the code generated for the GPU, the execution of the code, it's quite faster than the rest of them, of the other ones. Okay, so we now established that we are faster than the modeling tool, and that we can leverage some different execution architectures, such as multi-core CPUs and GPUs. So how do we compare to other similar tools? So I did some other experiments. In this case, I used Python and scikit-learn to generate a support vector machine model with a multi-class model to generate the PMML, and using the multi-target compiler, I generated some CUDA-C code for using the GPU and compare against a tool which is called Thunder SVM. It's a Python tool for building and for building support vector machine models using the GPU and the CPU. So this time I'm comparing GPU versus GPU tool versus GPU generated code, and I did different experiments. In the case of the graph that is on the left side on the bottom, barely the generated code is a bit faster than Thunder SVM, but on the rest of them it was quite faster than the actual Thunder SVM tool. And in fact, I think I didn't have space to put it here, but in some cases, the generated code had a better management of memory, because with a bigger scale factor in Thunder SVM it didn't work, and the CUDA compiler, I did some optimizations to use a more efficient management of memory. And if the memory doesn't fit entirely in the GPU memory, it works in batches. So okay, so that's with the empirical evaluations, and then we go to the conclusions, where we present a compiler to translate machine learning models to source code, and this code can be embedded into operational environments. We can automate the deployment and one important aspect of this approach is that it is self-contained. You don't need to install any external libraries to work. And we can effectively reduce the time to deploy. And we can also leverage sequential and parallel architectures. If you're looking for efficiency, this is another advantage of this approach because you can use multi-core CPUs or you can use GPUs, and it will give you performance improvement if you are using just your modeling tool. And another advantage of the compiler is that the modularity allows to easily extend for new types of model or for new front ends or new target languages if that's the case. And that's it. That's my reference, and thank you for your assistance and any questions that you might have. If you would like to know more details, or maybe I would expect some questions, but I have here an example of the PMML. I mean, this is not my development, but it's part of the design. It's just stating the definition of machine learning model, where we have all the layers, all the numbers, all the coefficients, and that's it. This is an example of the generated code with C. This is just an example, an excerpt, because I could not put all the code in one single page. And that's it. These are the datasets that I use and the computer equipment that I use, and that's it.
Thank you so much, Oscar.
Thanks.
Let me open the questions and answer part of our seminar. So whoever wants to ask, just raise your hand or just switch on your mic and ask questions. So for a starter, I may have one.
Okay.
Just a general question about the software that you demonstrated. Is it available, like open source, documented, and ready to use for others, or it is some closed under development version?
Yeah. Well, for now, the full version, it's closed, but let me see if I can exit this. You are still seeing my screen, right? Yes?
Yes.
Okay. The whole code is not open, but there's a small part of it in, sorry, let me just open this. Well, there is an R package, if you are seeing my screen, which is called glm.deploy, which does something similar of this. You can download the package in R, and then you can feed this package a generalized linear model, and then you can generate C or Java code. So this is what I have published. This is published and in the repository of R. And for now, I cannot say of what plans do I have with the project, but I hope that maybe I will publish it later. I'm still not sure.
And I have a related question, because in the scientific community, we have a similar problem as in the industry, that we want to have the predictions computed quickly. Right? Not only training of the model, but also the prediction. Sometimes you want to achieve quickly. And my question is whether your framework can be used for the purposes of the scientific community.
Well,
For instance, let's say we have a PyTorch model, and we would like to have a, let's say, faster version of it. And first question is whether the framework can deal with it and be, for instance, be used naturally in the HPC environment that we have here at the university. And the second question is whether it is possible to speed up also the training process when using, let's say we have a developed model, but it is not yet trained, and we would like to take advantage of the speed up for the training process. What would you say on that?
Well, the compiler only addresses the deployment task, so it only addresses the part of of generating predictions. So for training, I mean, it is not designed for training. Maybe you can use different accelerators for PyTorch, but it's not the case of the compiler. What I can say is that at the time that I did it, I started with this standard, which is called PMML. And then when I was almost finished, I realized that there was another standard launch, which is called ONNX, which is specifically for deep neural networks. So I thought maybe I leave that as a future work. It can be done. In here, instead of having a front end for PMML, I will add a front end for ONNX. And as far as I remember, you can use TensorFlow, you can use Keras, you can use PyTorch, and at least the most important tools, you can use them to train a model, and then you can export it to ONNX. And you can then, I can be able to use it as a front end and use the multi-target compiler to generate code. Of course, this will require implementing some additional things because I already have implemented neural networks in the intermediate representation, and I already have some templates. So the short answer is yes, it can be done. I will need to add a front end, and I will need to add maybe some specific operations for deep learning neural networks, such as, for example, convolution and another specific ones. But it is possible to do.
I see. And I have a quick question about on page 10. You mentioned that the models A and A prime should be semantically equivalent. What does it mean semantically? You mean that they should give the same answer for the same question, or right?
Yeah, which it must mean the same. That's the way that that is explained here. It's and it's one part of the empirical evaluation where I check if with some input it gives me some output, the modeling tool. And for sure, if the generated code should give me the same output as the modeling tool, and if that is the case, it means that the generated code is correct. Of course, I found out that it is the same. I could achieve the same output, but just in specific cases where the mapping of data types are different, there's a slight difference in decimals, but it's not relevant. I don't know if I explain myself, but maybe with Python you have float 32 or float 64, and with CUDA you have some data types, and with C you have some data types, with Java some data types, so on and so on.
Sure. And would it work with some novel models? You mentioned that there's this NX standard, and how it is strict about the choice of the modeling tool, because we have some novel ideas for instance, for the deep neural networks, and what needs to be done to make it compatible with
Well,
your framework.
Well, to be clear, this standard was designed before the rise, let's say, of deep learning models. So it became used mainly for general linear models or tree type models or support vector machines or other kinds of models, but not deep neural networks. There was an effort to be compatible with deep neural networks, but it's not used for, as far as I know, it's not commonly used for deep neural networks. The other standard that I mentioned, this is used for deep neural networks. It's called ONNX, and I think that if I go back in time and redo the compiler, I will try to address that standard too. But because to be honest, PMML it's not so relevant in the deep learning domain.
Right, fair enough. I don't see anyone who wants to ask question, so I think it would be nice if you hang around here in Luxembourg for still for a while to develop your toolkit, and perhaps it could be also useful for more advanced models that are sometimes used in our community. That would be really useful. Also, that would be perfect if you could let's say make it possible to generate also the training model. That would be much faster than the ones that we currently use. That would be super useful. Sometimes you are waiting several weeks to finalize the training, and if it can be sped up by a factor of 10 or 100, that would be a perfect world.
Yeah, of course. I mean, I would like to go back and this is a work in progress, of course, and every day we see new stuff. Maybe I didn't mention, but this work is within the context of my PhD dissertation, which was 2 years ago. But the surprising thing for me is that it is still a relevant subject. But yeah, I would like to go and implement some things in the deep learning domain.
Right, great. Thank you so much, Oscar, for your effort and for presenting us this framework and this topic. I can see some mic switched on.
Yeah, actually, I have a question regarding the.
Okay, great.
Oh, I have a question regarding the model exporting from the Python to PMML. Is there any tool to do it, or did you do it manually?
Well, I don't remember from memory right now, but if you look PMML, if you search PMML Python, there's a package for Python. So you can use scikit-learn and then export the model to PMML.
Yeah, okay. Thank you.
You will find it easily.
Yeah, okay.
If you are using scikit, most of the algorithms are compatible to exporting to PMML.
Yeah, okay. Thanks.
Yeah, you're welcome.
Any other question? Yeah. Okay, Oscar.
Okay.
You wanted to say something?
No, I just wanted to remark that it is quite convenient to have a standard like this, especially if you have separated teams, where you have the data scientist team and you have the programming, let's say, or software engineering side, and trying to explain them the model with just an informal description is not so easy. So if you can export the model, maybe by using PMML or in the deep learning domain with ONNX, you have a generated document from the tool, and you can start from there instead of trying to explain in paper or just by speaking what are you obtaining from that.
Right. And do you think it is possible to have, if you could send me the link to the, I don't know, website or repository in which one can, let's say, read more on or access
Yeah.
this framework?
Yeah, for
I
sure.
think it will be very useful to link it as a additional material to
All the
presentation on our
sure. Yes. All
website.
the experiments that I present here are in papers that I publish. So I can send the links of those. I can send the link of those, and I can send the link also of the standard, so you can check and see if you can use it in your daily basis work.
All right, great. Thank you again, Oscar. Thank you
Thanks.
all for your for coming here today, and have a good day and a good rest of the week. And I will keep you posted about future machine learning seminars.
Okay.
Bye bye.
Bye.